Chapter 9, Electrons and Atoms and the Periodic Table. We begin by looking at energy in the form of light. We have noticed that light coming from electrically excited gases that are in light bulbs, such as neon lights, they give us a clue that the energy in atoms is quantized. That is, it has only certain values. Because when we light up the particular bulb, this may be hydrogen, then we only see a few lines bright lines in the spectrum, not a continuous spectrum. And note that each specific color has a specific energy. Light can be thought of as a model as a wave. In this wavelength, we have the distance from crest to crest, and all electromagnetic radiation moves forward at the speed of light, 3 times 10 to the 8 meters per second. The visible light can be passed through a prism, and it will be broken down into the spectrum of the colors red, orange, yellow, green, blue, indigo, violet, Roy G. Biv. And we associate the short wavelength high energy with violet, and the long wavelength lower energy with red. So it's important. Red, long wavelength, low frequency, low energy. Violet, short wavelength, high frequency, high energy. The electromagnetic spectrum, of which light is only this tiny little bit, goes all the way from very low energy of radio waves with long waves and to gamma rays with very high energy and very short. And so this electromagnetic spectrum is an important measure of energy. Each element we know about emits its own spectrum, emission spectrum. Mercury appears blue because its lines are predominantly in the blue region. Here's hydrogen, which appears a slightly pink color. The spectra are called the fingerprints of the elements. That's why we can look at light coming from the sun and know what elements are present. White light is continuous, as this is shown here, emitted at every wavelength. The emission spectrum of individual elements includes only specific wavelengths. This is hydrogen, shown with 4 of its lines, helium with a few more, neon with more. Light emitted by hydrogen contains just distinct wavelengths that are specific only to hydrogen, shown here. Niels Bohr developed a simple model to explain why hydrogen emits only line spectra. The model he created was an atom with the nucleus here and with orbits in which the electrons reside around the nucleus. The energy of each of these orbits was specified by a quantum number, 1, 2, 3, and these energy levels are somewhat like the steps in a ladder, each at a specific distance from the nucleus. The further out you go, there's less separation. So this is the example, the ladder. N1 is pretty close to the nucleus and a pretty big jump to the N2, and smaller the further out. Energy levels close. These energy levels in the atom are sometimes called electron shells. What happens is that energy comes in and strikes an electron, excites it, kicks it out to some level. It can't reside in between levels. Once it's at that level, at some later time it relaxes, and when it drops from that level back to this level, this specific amount of energy is emitted as a light of this particular wavelength. Of course, if it jumps from this level to this level, you're going to have much more energy release, and it'll be very short wavelength. So the energy here shows up as a line in the spectrum. Here, in fact, is an explanation. When an electron jumps from n equal 3 to 2, that's not a whole lot of energy. It's in the red if it jumps from 4 to 2, it's in the blue-green. If it jumps all the way from 5 into 2, it is. Others, if it jumps from, say, 3 to 1, that's going to be in the ultraviolet. The atom now is, we're going to look at the quantum mechanical view of the atom with orbits that are kind of probability clouds. So within a shell, there are subshells, and these are called orbitals. The orbitals are a specific shape and orientation. They are designated by letters S, P, D, and F. For instance, orbitals with a S subshell have a spherical shape, shown here. And of course, the sphere has no orientation. Orbitals with a P subshell have a dumbbell shape, and they can be orientated in 3 different ways. So we have 3 p orbitals, one in the z direction, one in the x direction, and one in the y direction. And orbitals with a d subshell generally have 4 lobes in different planes, and this z subshell. Electron configurations, how electrons occupy these orbitals. A configuration shows the occupation of orbitals by electrons for a particular atom. The electron configuration for a ground state hydrogen atom is 1s1, 1 indicating the electron is in the lowest first shell, and it's in an s orbital, the sphere-shaped one, and there's only 1 electron there. This simply tells us that hydrogen's single electrons is in the 1s orbital. Another way of representing electron occupying orbitals is called a orbital diagram. And note it's very differently. A box is drawn for the orbital. For instance, the hydrogen, this is the 1s orbital, and we put an arrow in it to represent 1 electron of a certain spin. In orbital diagrams, the direction of the arrow pointing up represents the electron spin, which is a fundamental property of electrons, and orbitals may have no more than 2 electrons with opposite spins. So if you have 2 electrons in the same box, one has to be spin up and the other one has to be spin down. Here's the energy of filling the orbitals. The lowest energy is 1s, can have 2 electrons, then 2s, then 2p, then 3s, 3p, in this kind of zigzag manner. After the 4s, you can start filling 3ds, then 4p's, and then 5s, and then 4d. It'll become clearer to you. The helium atom has 2 electrons, so therefore its electron configuration is very simply 1s2. First shell, the S-shaped orbital with 2 electrons. Its orbital diagram shows the 1s orbital with two arrows. Lithium has 3, and so therefore it fills the 1s, and then the next one to fill is the 2s, and they only put 1 in that. 1s2, 2s1, orbital diagram. For carbon, it has 6 electrons. It'll be 1s2, 2s2, 2p2, and it would be diagrammed out like this. Here's the 1s with the 2 electrons, the 2s with the 2 electrons, the 2p, and there are 3 p's available. 2p is got 1 in this orbital and 1 in that. Notice that electrons of a given grouping occupy the orbitals singly rather than pairing up. And remember that the number of electrons in a neutral atom is equal to the atomic number, which you can get from the periodic table. The noble gas. When writing electron configuration for elements beyond neon or beyond any other noble gas, it's a very long process, and this can be abbreviated simply by using the brackets of the noble gas. It's all filled. For instance, sodium has 11 electrons. Here's the longhand, 1s2, 2s2, 2p6, 3s2, but notice that these are filled, and then we move up to that. And that is the configuration of neon. So we can just say neon, which represents this amount, and then the 3s2 are the outer valence. We have valence electrons. Those are electrons in the outermost principal shell. Principal, the highest number, principal quantum number. And they're important because they're the ones that are involved in bonding. Electrons that are not in the outer principal shell are called the core electrons. Let's look at silicon, which has 4 valence electrons. And its particular electron configuration would be 1s2, 2s2, 2p6. That's its core group. And then we have the valence. The outermost shell is the third shell, 3s2, 3p2. So here are the 4 valence electrons. These are the core ones. Selenium has 6 valence electrons. Notice here's the core, and then we actually arrive at the 4th level with 4s2, and then we have gone back to fill the 3rd level, which is underneath the outer shell. It's not the part of the principal quantum number, and so therefore selenium counts as having 6, 4s2 and 4p2. These are all part of the core, the blue. All the electrons, including those of 3D, are called core electrons, other than the valence electrons. The elements within a column of periodic table all have the same number of valence electrons and similar outer electron configurations. Note in 1A they all have 1 electron in their outermost orbital. 2, they have 2, 2s2, 3s2. And you notice then we skip over through the transition elements and we get over to the 3A group, and we see that it has 2s2 filled S and then 2p1, and we continue. They all have the same outer electron configuration. Very important to note. We can use the periodic table to write the electron configuration. We'll start with nitrogen, which has 7 electrons, and we write it out 1s2, 2s2, 2p3. That's 7. To do the orbital diagram, we use the 1s, 2 electrons, 2s, 2 electrons, and then the set of p orbitals, which are there always 3 of them, put 1 in each orbital. Oxygen, we have 1 more electron, so it gets added to the 2p level. Fluorine, it gets added to the 2p level. And neon, the 2p level is now filled, and this is the noble gas. The electron configuration neon represents the completely filled shell, n equal 2, principal shell. A pattern exists for writing the electron configuration, which can be gotten from the periodic table. As we look at the periodic table, we know that we have all these in blue representing adding a s electron to whatever level we're in. Whatever shell is the outer shell. And then these are the d block. You're adding d electrons. They're usually underneath the outer shell. And then these are the p block. And this is the f block. For example, we would like to write the electron configuration for aluminum. Well, we could simply say it's neon. Then once we go beyond neon, just use the periodic table. We are going to the 3rd shell, so it'd be 3s2, going over to aluminum, 3p1. So one can write the electron configuration very easily of any elements, say like bromine, start with argon, and then go 4s2, and then go 3d10, and then go 4p4. And here's again a review. If we want to write the electron configuration, the very best thing is for, say, for phosphorus, we go back and we have the core of neon. And then in the outer shell, the same row that phosphorus is in, it's a 3s2. We have no d electrons, and 3p3. So here's the correct configuration for phosphorus. Neon core, 3s2, 3p3. 5 valence electrons. Elements attempt to achieve inert gas configuration or noble gas. Sodium tends to lose electron to form sodium ion, and fluorine tends to gain an electron, become a minus anion. And by doing this, both obtain neon noble gas configuration. Some elements like to give away metals, mainly those are metals, and they have only 1 or 2 electrons to give them up. Others, like nonmetals, like to pick up electrons. Calculation shows that with 8 valence electrons, or 2 for helium, we have the noble gas configuration, and they're chemically stable. They're relatively inert because they're not looking to gain or lose electrons. So here their outer shell. This is a filled second shell, a filled third shell, filled fourth shell, etc. The alkali metals, group 1, are the most reactive metals because they only would like to give away that one outer electron. And when they lose that electron, they obtain a noble gas configuration. So that's why group 1 metals tend to form a +1 valence. The alkaline earth metals, group 2A, like to give away 2 to attain their noble gas configuration. The halogens way on the other side of the periodic chart, right next to the column of noble gases, group 7A, or 17, they can gain 1 more to fill their orbital, become like the noble gas configuration. So they tend to become an ion charged -1, picking up 1 electron to get to the inert or noble gas configuration. Here are elements of the periodic table that have no unpredictable charges. All these have +1, all these have +2, these have +3, and these in the upper level they have -3, -2, -1. Let's look at the periodic trends. For instance, the size of the atom. It's stated that as you move to the right across the periodic table, the atom's getting smaller. There's a rationale for this. You're adding electrons to the same shell. For instance, shell 2. This is shell 3, but you're adding electrons to the same shell. So you're not adding into a further out orbital. And the nuclear charge is increasing. Atomic number of lithium is 3, so we have a +3 nuclear charge drawing those electrons in. Here we have now a 4, +4 charge, +5, +6, +7. I think I have that right. Therefore, what is happening is the nuclear charge is increasing, drawing the electrons closer, and the electrons being added are to the same shell. Now when you go down the periodic table, the size increases because here in lithium, the outer electron's in the second shell, and then the next, in sodium, you put it in the third shell. That makes the atom bigger. Fourth shell. Ionization is another important concept because to take the neutral atom and form the ion, generally energy is involved. And so therefore, it's usually the energy required to remove the outermost electron from an atom. Well, obviously it's going to be increased as you move to the right because that electron is getting closer to the nucleus, harder to remove. As you go down, the energy required is going to decrease because the electrons are getting into the next shell. So small atoms have very high ionization energy. Large atoms have lower ionization